Welcome everyone to today's webinar. It's my great pleasure to introduce today's speaker, Eojin Han, joining us from US. So Eojin got his PhD from Northwestern University in the Department of Industrial Engineering and Management Science, and then after that joined as an assistant professor uh, to Southern Methodist University, but he wanted to explore more. So then he joined the IT Analytics and Operations department in Mendoza College of Business at University of Notre Dame in US. His research is focusing on robot optimization with applications to healthcare, supply chain, and service systems, and he has also publications in leading journals like Operation Research and Management Science. And so it's a pleasure having you here, Eugene. And without further ado, I want to give the control of mic and screen to you.
Sure. Thanks so much for a nice introduction and your invitation to this webinar series. My name is Eojin. I'm gonna talk about my research on like developing another classes of decision rules with the aim of obtaining more scalable policies for solving multi-stage robust optimization problem. So this is a joint work with my PhD advisor, Omido Hadani, who's now in industry. Yep. So I'm broadly I'm broadly interested in dynamic decision making under uncertainty, and those problems are just everywhere in many application area. For example, in supply chain management, managers need to make inventory decision, like how to replenish how many inventories that they need to replenish their system by considering the future uncertainty over time. Some products may be correlated, and then they need to consider supply chain structure. So basically, like this inventory management is like a natural problem of sequential decision making under uncertainty, and power system and energy. These are another application area. So at each time period, we'll give a multiple time period, and at each time period, we need to make a decision on how much electricity they need to produce from one generator, from another other generator, like about this dispatching decision and so on. And of course, these decisions are also sequential because they need to deal with uncertain demand over time and like other other sources of uncertainty, such as like a weather condition in the context of renewable energy. So basically, most decision-making processes are sequential, meaning that like the future decision should be dynamically determined. It's not just for the current period, but this decision should be made by anticipating what would happen in the future. And that's exactly why dynamic decision-making under uncertainty, those problems are hard. And there are lots of different modeling techniques for solving this problem, but just like many of the audiences in here, I'm interested in robust optimization problem, especially two-stage robust optimization problem. So we have first stage X and second stage decision Y. X is decided before observing an uncertain parameter C, and then the second stage decision Y is made after making an observation of an uncertain parameter. And we assume that the second stage decision is obtained by solving a linear optimization problem where the uncertain parameter and X depends or affects the constraint of the second stage problem. Um, so based on that, the two-stage robust optimization problem can be formulated as follows. So we're having a min, max, min structure. So we need to make a first stage decision X, and then we observe an uncertain parameter C, which assume that we're gonna make an optimal decision that minimizes the worst case cost. So that's why we're having max. And then after that, we're having another mean operator which is for the second stage decision. So it's a pretty general formulation of two-stage problem, and we assume that this A of Xi and H of Xi, they are given as an affine function in Xi. We assume that uncertainty set is second order conic representable, meaning that it covers all polyhedron and all commonly used uncertainty sets such as ellipsoids or budget uncertainty set or intersection of these two and so on. And in general, solving these two-stage robust optimization problem is NP hard. And this result has already been shown more than 20 years ago. And the reason for this difficulty of solving two-stage robust optimization problem is that it is hard because the second stage decision often has very complicated dependence on Xi. So it means that it is given as like a very sophisticated function, and another so like given this difficulty, one approach to approximate the two-stage robust optimization problem is to use decision rules, which restrict the second stage decision to be given as like a simple function of uncertainty. Okay, so one popular and widely used approach for using this decision rule is what's called as a linear decision rules. So as it's implied by its name, it models that the second stage decision is given as affine functions of uncertain parameter. And now the problem converts the two-stage problem into a single stage problem where in the single at the first stage, we decide the first stage decision X along with the optimal parameters for the linear decision rules. Those are W and capital W here. So basically now, like under the LDR, now we don't have min, max, min structure, but now we only have min, max structure, which we can solve uh, efficiently for many different cases of uncertainty sets. Okay, so linear decision rule, although they are very popular and widely used, those are not the only option that we are given to approximate the two-stage robust optimization problem. So there are a lot of many other existing methods in the literature, and they can be, in my opinion, they can be plotted in the space of optimality and computational tractability. Okay, so LDR is one extreme case where computational tractability is much better than many of the others, whereas the optimality, sometimes LDR would not perform very well. And on the other extreme is an exact approach, which aims to solve two-stage problems to optimality without too much concern on computational tractability. So those are based on just enumeration of uncertainty sets or column generation or column and constraint generations and so on. And many other decision rules have been proposed in the literature between these two extremes. For example, there has been like some piecewise linear decision rules by parametric lifting methods. So this is also a lifting-based method, but I would say these approaches are different from our non-parametric approach. So I'm going to elaborate more on how these approaches are different from ours in the later slides. And there's also a partition-based approach, which basically the idea is to take the partition of uncertainty set into smaller pieces and then implement linear decision rules for each piece. So it includes some work by Posteg and Den Hertog and for Persimmons and Dunning. And another approach could include using copositive programming approaches for quadratic decision rules or piecewise linear decision rules by Zhu and Hana Susanto. And there are also some polynomial decision rules, which uses some theory of polynomial optimization to obtain decision rules of having a certain degree of 2 or 3, something like that. So in my opinion, many of these available approaches in the literature can form like a curve, have an efficient frontier between optimality and computational tractability. And along with this existing work, our goal in this paper is not to solve the problem to optimality, but instead, our goal is to extend this efficient frontier which may be better than some existing method in terms of optimality, but our goal is to obtain these policies without losing too much computational tractability. Okay, that with that goal, we will describe how our non-parametric lifting framework will be helpful to achieve these goals. Okay. All right, so I'm gonna provide like basic lifting framework for nonlinear decision rules first, and then we will describe two of our non-parametric lifting, set-driven lifting, and dynamics-driven lifting. I will briefly discuss how we can extend these lifting techniques to multi-stage problems, followed by some numerical results and conclusions. Okay, and if you have any question, you can just please like leave the chat message, or we can be more interactive during the presentation. All right. Yep. So basically, the lifting framework is to obtain a generalized decision rules of this form. So we have the first two terms are the same as the linear decision rules, but we have this additional term here for a given nonlinear function g, and the goal is to obtain such policies by lifting the original uncertainty set u to u bar in higher dimension, and just simply compute linear decision rules on those lifted set u bar. So basically, this is the problem for computing generalized decision rules. So you can see that like it looks pretty much the same as the LDR. The only difference is that we're having this U bar in higher dimensions. So we're in the higher dimension. So we're having another uncertain parameter eta, and then those in the max operator, in the objective function, and in the constraint. That's the only difference. And then the natural question following this formulation is that how we should define this lifted uncertainty set U bar. And fortunately, we have some result that an optimal, this is not my result, by the way. This has been already established in some of existing works in the literature. So it shows that an optimal policy of a form here. So if you're given G, and then if you want to compute an optimal policy of this form, then you can solve this problem by defining the lifted uncertainty set U bar as this convex hull of the graph of G. Okay. So this is certainly a good news because now we can see that we have a convex formulation of a lifted uncertainty set to compute the optimal policy of this particular form when nonlinear function G is given. But on the other hand, uh, the, the 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 downside is that even if U is convex and the function G is convex and has some nice properties, exactly characterizing this U bar, which is given as a convex hull, is computationally hard. Okay, so this proposition is a theoretically nice result, but in practice, it's challenging to be implemented for most cases. And basically, based on this, like there has been some framework or procedure of constructing generalized decision rules by lifting. Um, so the first step is to figure out the nonlinear function g. So this is a kind of extreme case where this g can have this non-typical shape. But like the first step of this parametric lifting is to find this nonlinear function. And then the second step is to construct the lifted set, but given that this convex hull characterization is not very efficient for most cases, the goal is to define this U bar as a superset of this convex hull. Okay, so it might be great if we can exactly characterize this convex hull in a tractable manner, but in other cases, but in most general cases, it is fine just to obtain a superset of this convex hull. We need to make sure that our lifted set should be strictly, not strictly, but larger than this convex hull. And then the last step is to compute the generalized decision rules by just implementing LDR on this U bar. Okay, so that's the basic idea. of parametric lifting. And I'm mentioning this as parametric lifting because this nonlinear function should be given in the first step without taking a look at the actual two-stage robust optimization problem that we need to solve. Okay, so as opposed to these parametric lifting methods, our non-parametric lifting methods are different. So we will find this nonlinear function g by extracting some information from the problem. So we will see how the uncertainty set looks like, what the cost coefficients are, how the constraint looks like for the second stage problem, and then we will try to use this information to figure out which nonlinear function g will be more efficient for lifting. Okay, and for the second step, so after this G, we need to define our lifted uncertainty set. But our goal is to describe this U bar in a computationally scalable manner. So theoretically, it will be as computationally tractable as linear decision rules with a little bit of additional number of uncertain parameters. And then we will also define such U bar in a way that we can come up with or we can establish some performance bounds. Okay, so those are the concept of our non-parametric liftings. Okay. All right, so with that point of view of parametric and non-parametric lifting point of view, many of existing methods in the literature can be called as a parametric lifting method because they are given some particular form of function, which is completely independent of the two-stage problem for a given instance. And many of them actually require some particular assumptions on the uncertainty set, such as hypercube, or like linear and norm constraint and polyhedral with known extreme points or things like that. But they are computationally tractable and they can be extended to multi-stage problem. And one different another existing work which is slightly different from the other method is this primal dual lifting proposed by Giorgio in their OR paper. So it can be called as a non-parametric lifting framework because they develop an algorithm which finds an extreme point to be lifted by solving some approximate problem of the two-stage instant over multiple iterations. So basically, their goal is to obtain a sequence of piecewise linear decision rules over iteration that can possibly solve two-stage problem to optimality or to get a near optimal solution. However, their uncertainty set also requires some assumption to be given as a polyhedron where all extreme points are explicitly known. And to my understanding of the algorithm, it performs very well for numerically, but computational tractability is not guaranteed, and multi-stage extensions are not provided. Okay. So as opposed to these existing work, our two liftings, set-driven liftings and dynamics-driven lifting, those are both non-parametric. And they can work for all SOC representable sets, and then they preserve tractability, and they can be extended to multi-stage problems with some performance bounds. Okay, so now I'm going to explain what the set-driven lifting and dynamics-driven liftings are. So we will start by set-driven lifting. So set-driven lifting is based on lifting an extreme point for a given polyhedron. So I'm going to explain that first, and then we will generalize it to general SOC representable set. So this is something we call as simp lifting. So when a polyhedron is given with all known extreme points, then a simp lifted set P bar is simply given as a convex hull of points in higher dimension, where the additional vectors are assigned to be 0 for the first n+1 extreme points. And for each additional extreme point, we're assigning the unit vector in higher dimensional spaces. So basically, this is an example of the simp lifting. So when we are given like a polyhedron with 4 extreme points in two-dimensional space, the simp lifting procedure will lift this rectangle to a simplex in three-dimensional space. So basically, this is the idea of simp lifting, and you can see that simp lifting always lifts polyhedron to simplices in higher dimension. And if you're familiar with the robust optimization literature and decision rules, if you run linear decision rules over simplex uncertainty set, then optimal decision rules are always obtained. So meaning that if we do simp lifting for any polyhedron, then we can solve two-stage problems to optimality because they are always simplices in higher dimension. So that seems to be a good news, but on the other hand, the the downside is that this lifting all extreme point is intractable in most general cases. And that is simply because in general polyhedron, the number of extreme points can be exponential. Okay, so we cannot really lift all this exponentially many number of points in practice, so that this is not really a practical um, step to be implemented. So our set-driven lifting is based on simp lifting, but it doesn't really lift all the extreme points. So our set-driven lifting is instead given by fitting a polyhedron P within an SOC representable uncertainty set U. Okay, so this can be done by 4 steps. So let me explain step by step. So let's say the ellipsoid uncertainty set is given in the two-dimensional space. Then the first step is to find a polyhedron P with all known extreme points, which belongs to the original uncertainty set U. The second step is to construct a simplifted set of that inscribed polyhedron. So it will be a simplex in higher dimension. And then the third step is to just inflate this image so that the inflated or dilated simplex can cover all this original uncertainty set. Okay, so if you make it larger, then it is possible that it can cover all the original uncertainty set. And the last step is just to define the set-driven lifting as a restricted image of this dilated simplex onto the original U. Okay, so this is how the set-driven looks like for this particular example. And the good news is that the set-driven lifting is tractable as long as our inscribed polyhedron has a smaller number of extreme points, because we don't really lift all the extreme point of the original uncertainty set. The extreme point that we lift is only the extreme point of the polyhedron. Okay, so whenever we keep the number of extreme points small enough, then it will be fine in terms of tractability. And then we can also show that this set-driven U bar induces piecewise linear decision rule. So when we are given all this extreme point, then we can show or we can explicitly characterize what are the corresponding piecewise linear decision rules for this set-driven uncertainty set. Okay, so we're basically going beyond from linear to piecewise linear decision rules. Okay. But the question is how we should choose this polyhedron, which should be inscribed within U when our uncertainty set is given. And for that, we need some theoretical result. So we establish performance bounds of this set-driven lifting with this assumption of the first stage decision should belong to a cone, U is non-negative, and then all this technical assumption. So these assumptions are pretty like common in robust optimization literature of analyzing the performance of decision rules. So I think it's pretty general. And then under this assumption, we can show that the objective value of the set-driven lifted set U bar is bounded by this factor times Z star. So Z star is the optimal value of the two-stage problem. So this is a bound, and then this parameter rho and S describes the geometry of uncertainty set. So I'm not going to give like an explicit definition of these parameter, but you can understand these parameter as some parameter only related to you. And lambda is the dilation factor of P with respect to you. So this is something that we can control because uh, when we choose different polyhedron, then the dilation factor will be different. Okay. So that, and then we can also show that this bound is actually increasing in the dilation factor, meaning that in order to achieve uh, the bound as tight as possible, we want to choose the inscribed polyhedron in a way that we can kind of minimize the dilation factor. Okay, so that gave us insight on how we can choose this polyhedron to define the set-driven lifting. So we have to take care of this dilation factor. Um, and this insight can be used to find some nice polyhedron for commonly used uncertainty sets, such as ellipsoidal uncertainty set or budget uncertainty set or intersection of these two. And our result extend the result of Bersimas and Bitcory in their math programming paper to generalized decision rules. So basically, they provide the exactly same bound for linear decision rules. But what we show here is that we can actually think of this logic in a higher dimension in set-driven lifted uncertainty set. And if that's the case, then we can have or we can preserve the same performance bounds for the set-driven lifting. Okay. All right. So this is the set-driven lifting. So this is one non-parametric lifting that we propose. And then the dynamics-driven lifting, the other one, is actually motivated after implementing this set-driven lifting for many problems during our numerical experiments. Okay, so in particular, we found out that the set-driven lifting can be less effective when the dilation factor lambda is large. And this is kind of expected result because our performance bounds depends on lambda, which is increasing in lambda. So if the dilation factor lambda has to be large, then we can expect that the set-driven lifting would not perform very well. For example, if the uncertainty set is given as a hypercube, then it is very hard to find a polyhedron with smaller number of extreme point with a small enough dilation factor. Okay. So this is one limitation, and another limitation of set-driven lifting is that it accounts for for some information of the problem, but it's only based on uncertainty set, right? So we haven't used any like objective coefficient or coefficients of the constraint, like any other problem parameters other than uncertainty set. We haven't used this information at all. Okay, so the set-driven lifting is completely independent of problem coefficient, and this can be another limitation of set-driven lifting in some cases. So actually, we came up with some example that we construct an instance of two-stage robust optimization problem with ellipsoidal uncertainty set, which is perfectly symmetric, such that if we do a set-driven lifting with a standard L1 ball inscribed within this L2 ball, then it solves the problem to optimality. But we can also find an L1 ball with which the set-driven lifting does not improve over linear decision rules at all. And this example shows the importance of accounting for the problem coefficient because the uncertainty set is perfectly symmetric, and then just based on the performance bound, any L1 ball will have the same dilation factor. I mean, like any standard L1 ball or its um, linear transformation will have the same dilation factor. And then we didn't really expect if we use, I mean, like under the same dilation factor, the performance will be different. But this example shows that even with the same dilation factor, the performance can be very different. Okay, some L1 ball can solve the problem to optimality. Some L1 ball does not improve over LDR at all. So that means we need to do something else to improve over this set-driven lifting in some cases, and that's the motivation of dynamic-driven lifting. So we were thinking of how we can use both the structure of uncertainty set and problem coefficient. And in dynamics-driven lifting, we wanted to figure out this information by using optimal linear decision rules, because optimal linear decision rule, they should be implemented on on a two-stage robust optimization instance. They may contain some information about the uncertainty set and the problem coefficient. Okay, so now we're going to expand more on how we can use these optimal LDRs to compute this dynamics-driven lifting. So let X star, W star, and capital W star be an optimal LDR of a given two-stage instance. And then under this optimal LDR, if you plug in this optimal solutions to the constraint, then we can observe that under the optimal LDR, the second stage constraints are satisfied by a hyperplane, because this is affine in Xi. Y of Xi will be affine in Xi under the optimal linear decision rule, and H of Xi is affine in Xi. So if you plug in this optimal LDR, then the constraint satisfaction of each constraint can be represented as a hyperplane. Okay, so for example, the nth constraint can be expressed as a single hyperplane. And we want under the LDR, this hyperplane is always less than or equal to 0. And if you actually visualize this hyperplane, then it will look like this. So U is ellipsoidal. This plane, hyperplane, shows our constraint satisfaction. So we want to make sure that this is always below 0, because we are solving robust problem. But depending on the way the hyperplane is constructed, at some point, this constraint satisfaction can be very tight. We want it to be less than or equal to 0, but it will be actually be 0, which means that the constraint is tight. But on the other side of the hyperplane, on the other side of the uncertainty set, let's say C2 star here, then it is possible that constraint satisfaction can be loose when this hyperplane is defined in this way. So what we want to make sure at this point is that we want the constraint to be just less than or equal to 0, but the actual constraint satisfaction is made here, which is far below 0. And that might be the source of having inferior objective value. That this will be a room for improvement over optimal linear decision rule. So that's the idea of dynamics-driven lifting. So we will use these hyperplanes, which is implied by the optimal LDRs, to heighten the constraint satisfaction and C2 star. So this is like a high-level idea of dynamics-driven lifting. And more formally, we can do this by using what's called as a set of basis vector. So basis vector is Vn. And then for a given basis vector, we define our nonlinear function as follows. So what the basis vector does here is that basically it kind of interacts with the matrix to find a subset of constraint or subset of hyperplanes that's going to be used for defining a nonlinear function. Okay, so for example, if this is a hyperplane for the first constraint, and if this is a hyperplane for second constraint, and so on, and if you choose a basis vector v in a way that this set will only return the first two of the constraint, then our nonlinear function will be defined as a pointwise maximum of these two hyperplane, which looks like this deflected form. And then you can see that if you use this deflected function, and if you define lifting based on this nonlinear function, then we can possibly improve the constraint satisfaction at this point for this constraint, at this point for this constraint. Okay, so that's the idea of dynamics-driven lifting. So by using this G function, we can formally define the dynamics-driven lifting as follows. So we are having additional parameter eta. Eta is given as the epigraph of G of Xi, and this is not this is a convex constraint because G is convex. And we have another linear constraint on eta. This is kind of like a budget constraint because we're imposing the upper bound on the sum of additional uncertain parameters. Okay, so This right-hand side gamma bar is called as the bound parameter in our paper. And this quantity needs to be computed first in order to implement this dynamics-driven lifting. But we need to make sure that this gamma bar needs to be greater than or equal to the optimal value of this maximization problem. So basically, this is a convex maximization problem because Gn of C is convex by definition. But it is a piecewise linear convex, so we can probably use mixed integer linear formulation or other like semi-definite programming based approximation for solving this problem. Or there are many other practical like ways of defining like a budget constraint in a way that we can compute, we can avoid like a heavy computation of solving this convex maximization problem. So there are some ways to do that with the goal of improving the computational efficiency. And then in the interest of time, I'm gonna skip those details, but more information should be available in the paper. Okay. All right. So another very good thing for our dynamics-driven lifting by using this particular structure of the budget constraint is that we can show that the dynamics-driven lifting can improve the objective value over linear decision rules by at least some quantity delta as defined here. So this is given as as this form, which includes some optimal objective value of some maximization problem. But this is a linear program, so we can solve it quite easily. And this B bar is a constant only depending on the matrix B, the recourse matrix B of the second stage problem, and the choices of basis vectors. Okay, so, and this quantity is guaranteed to be non-negative. So we can show that, and then we can also show that, or we can provide sufficient condition under which this delta becomes strictly positive. Okay, so for example, if our gamma bar parameter is strictly less than zero, uh, this holds pretty like this assumption holds for most of our implementation in our numerical experiments. So we don't think this is a restrictive assumption. And if you choose our basis vectors in a way that this inner product is guaranteed to be positive, then we can actually show that this delta is positive, meaning that our dynamics-driven lifting strictly improves over linear decision rules. And we think this is a nice result because there has been a lot of nonlinear decision rules in the literature, and most of them, by its construction, it is guaranteed to be performed at least as better as linear decision rules. But not many of them has provided the lower bound on the improvement. But this one has a bound on the or lower bound on the improvement, meaning that if we compute this delta, then we can kind of have a certificate. Then okay, so if we implement this dynamics-driven lifting, then we will outperform linear decision rules by at least delta. And actually, the actual performance is much better than delta, but having a certificate is always good for optimizers. So I think this theorem is a nice result. And this improvement delta parameter is easily computable. This is a linear program, and this is much smaller than the two-stage problem or the LDR problem. This can be done ahead of like solving or implementing the dynamics-driven lifting to see if like this quantify lower bound will be worth to implement the dynamics-driven lifting. All right. Okay. So I'm going to briefly explain how we can extend this liftings to multi-stage problem. So basically, multi-stage problem is a straightforward generalization of two-stage problem. So we're having like multiple stages defined as realization of uncertain parameter at that period, followed by the decision at that period. And then we will proceed to the next stage, next stage, next stage, and so on. So many multi-stage robust optimization problem in finite time horizon can be formulated as in this form. So we're having a multiple uncertain parameter. And then the one thing that we need to be careful, or that's slightly different from two-stage problem, is that we want to model this YT, the decision at period or at stage T plus one, to be non-anticipative, meaning that it should depend on uncertain parameter that has been realized previously up to that time. So our decision at period T should not depend on uncertain parameter that will be realized after that period. Okay, so this is a quite natural and practical, and that must be imposed to solve a multi-stage robust optimization problem. And one good thing for linear decision rules and many of nonlinear decision rule is that they can easily capture this non-anticipativity by just having this sum. So like we can just restrict this sum not just from all not across all time period, but we can just restrict it to uncertain parameter that is being observed up until that point, and then we can model this as a constraint, and then we can compute the LDR, non-anticipative LDR. So this concept can be generalized to non-anticipative generalized decision rules by using this function GT, which should be also given as a non-anticipative function. And by using this concept, we can define a non-anticipative lifting as follows. So we can define this non-anticipative lifted uncertainty set if this satisfy these two conditions. So basically, the first one is like for this lifted set to be a valid lifted set. So if you projected this to lower dimension, then it should recover this lifted uncertainty set. And the second condition is like a generalization of the proposition that we saw in the very in the introductory part of this talk. Okay, so it has some like smooth and natural like generalization. And by using this definition, we can also extend our set-driven lifting and dynamics-driven lifting. So remember that set-driven lifting, we need to have an inner polyhedron and which are associated with a nonlinear G hat. So in order to extend this set-driven lifting to multi-stage problem, we need to be more careful for inner polyhedron, choosing inner polyhedron for corresponding G, the nonlinear function to be non-anticipative. And we show in the paper that this step can be done for many general cases, and for some specific cases, more efficient, like set-driven lifting is available for multi-stage problems. Okay. And for non-anticipative dynamics-driven lifting can also be done by introducing non-anticipative basis vector. So this is also a generalization from two-stage to multi-stage. And then we were also able to extend our performance bounds result, like a strict improvement delta. They can also be extended to multi-stage problems. So in the interest of time, I'm not able to explain all this detail for multi-stage problem, but those are already in the paper. So I would refer to the paper for the details. Okay. All right. So now I'm going to introduce some numerical results. So we will have two application multi-item news vendor problem first. So this is a simple two-stage problem of managing like multiple inventories of multiple products. So in the first stage, inventory is all fulfilled. Those are first stage decision. And then the demand is uncertain. Like an uncertain parameter is the demand, which is realized after the first stage. And then after that, the inventories are updated and the cost is computed. Like depending on the shortage or leftover, we may impose some holding costs and the penalty cost for each product. And then finding optimal robust solution is challenging, especially when demands are correlated and uncertainty sets are not rectangular. Okay, so that's why this, in my opinion, multi-item use vendor problem has been considered a lot for many methodological papers in robust optimization literature. Okay. So we assume that multiple items are given. This is how we generate our cost parameters, and then the uncertain demand is described by like a factor-based model. So I believe this factor-based model is pretty common in modeling multi-stage, multi-item news vendor problem in RO literature. So we compare or implement this six policies. So LDR, set-driven lifting, dynamics-driven lifting, this iterative splitting by Postek and then Hertog, this LRC, this is a linearized robust counterpart. So this is not like about the decision rules, but this is another way of solving two-stage problems to optimality. So we included it as a benchmark. So this is by Ardestani Jafari and Eric Delage. And the last one is QDR. This is a quadratic decision rule, which I introduced in the presentation. This is by Zhu and Hana Susanto. Okay, so we implemented and compare all the six policies when the number of item is 60. So on the x-axis, we show the log scale of computation time from 1 second to 10,000. And on the y-axis, we're having the relative optimality gap from 0% to 100%. So closer to being closer to 0%, meaning that the problem is being solved closer to optimality. So we have LDR, set-driven lifting, dynamics-driven lifting, iterative splitting, LRC, and QDR. And you can see that if the number of item is 60, then there is a clear trade-off between optimality and computational tractability because these policies are based on semi-definite and composited programming, and they obtain like near optimal solution, but they have to invest a lot of time. Let's say 2000 between 2000 and 3000 seconds. This is about like a 40 minutes or 15 minutes. Uh, but our SL and DL, it has a decent improvement over LDR by decreasing the optimality gap from 40% to like 12, 25 or 28%. But the additional computation time is just a few seconds. So SL is obtained within 10 seconds. Dynamics driven lifting is obtained within a minute. Okay, so that's what's happening in 60 items. And if you increase the number of items to 80, then you can see that LRC and QDR is now out of computational limit. So we set the computational limit as 3 hours, and then it was not able to return a solution within 3 hours. And then you can see that LDR, SL, DL, and IS, those are only implementable for 80 item. You can see that the similar improvement happens when number of item is 80, and but also the computation does not really increase that much. So it is still implementable in 30 seconds for SL, around 100 seconds, I would say, within 2 minutes for dynamics-driven lifting. So you can see that like SL and DL, those non-parametric lifting methods are more scalable. It doesn't really solve problems to optimality, but if you want to improve this over LDR with a decent increase of computation time, then SL and DL will be proper methodologies for doing that. Okay, so this is our result for multi-item news vendor problem. Another problem we did in numerical experiment is multi-item, multi-period inventory control. So this is essentially dynamic version of the news vendor problem where the unmet demand is backlog and the leftover stock is also preserved over the next period. So this is the uncertainty set that we use. So we use this mu t as a nominal demand, and then this is an uncertain factor, zeta t. Zeta t kind of has like infinite norm constraint, one norm constraint, one norm constraint across the time period. So uh, basically, this is a polyhedral uncertainty set, and then this mu t is generated from autoregressive processes to model potential non-stationarity in order to be more in order to be more relevant to practice. All right, so this is our result. So I is the number of items, T is the time period. We implement LDR, set-driven lifting, dynamic-driven lifting, and iterative splitting. Um, and then you can see that the objective improvement of set-driven lifting and dynamics-driven lifting is quite significant over LDR. So around 30% for SL, like 20 to 25% for DL. And you can also compare the computation time. So SL and DL, like they obviously took more time over to compare to LDR for obtaining these policy. But if you compare this computation time of set-driven and dynamics-driven lifting to the iterative splitting, then you can see that it's much more computationally efficient than this partition-based approaches. So for example, like for the case of 6 items and 30 time periods, like iterative splitting is out of memory or out of computational limit, like computational time of 3 hours. But our SL and DL, we can improve over LDR within 30 minutes for DL, around 30 minutes or for dynamics driven lifting, and around 40 minutes for set driven lifting. Okay. Um, so we can see that the set-driven and dynamics-driven lifting improve over LDR while maintaining computational tractability. Okay. All right. So this should be the end of the talk. So we propose two non-parametric lifting methods for solving multi-stage robust optimization problem. So the set-driven lifting uses uncertainty set, and we have like geometry-based performance bound. The dynamics-driven lifting, we try to use the information implied by uncertainty set and its interaction with the constraint by using optimal linear decision rules. And using this optimal LDR, we were able to provide a condition under which this dynamics-driven lifting can strictly improve over the linear decision rules. And we did some numerical experiments to demonstrate the computational scalability of our non-parametric methods. So the paper is already out after a long review process, and then you can, but for more accessibility, I'm having a QR code here to go directly to the link of the paper. Okay, so this should be the end of my talk, and I'll be happy to take any questions.